In our study so far of Riemann integration for scalar valued functions of multiple variables, I've said a few times that the domain A is a little bit more interesting than it is perhaps for single variable functions. In this lesson, we are just going to look at one particular notion that you might associate to a domain of integration. And this is the idea of volume. I wrote up here general volume because it's going to take some of our geometric intuitions and try to grow them with this mathematical definition that I'm about to take you through. Okay, so this whole lesson is really just thinking about A as a subset of Rn, where A is a bounded set which may serve as a domain of integration for some function f. We are not going to have any such functions f in this video, it's only about A. To study A, we do introduce in this new function, which we haven't seen before. This is called the characteristic function of A. You will sometimes see it called the indicator function of A. I typically call it the characteristic function. The notation for this function is typically 1 subscript a. Sometimes that 1 is boldface, but you should recognize it now when you see it. And it just answers a yes-no question. Is the input in A or not? If it is in A, then the output is 1. If not, the output is 0. So it's just a binary output. Then what we do is say, okay, take your domain A, which might be nice or it might be kind of strange looking, but it's in, say, some subset of Rn and it's bounded. As we've discussed in the past few lectures, take A and enclose it in a nice n-dimensional rectangle. So again, I use that word rectangle to mean the rectangle that you would associate to the correct size space. So here it looks like a proper rectangle. In R3, it might be a rectangular cube, but we discussed that in previous lectures. Now, is the characteristic function of A integrable over, say, S? And then it's like, what does that mean again? It means that, if I took every possible partition of this domain, computed all of the upper sums of this function. So this is the function now that we're looking at integrating. If I computed all of the upper sums of this function with respect to every possible partition of this enclosing rectangle, and then took the inf of that to get the upper integral, compared that to the supremum of the set of all possible lower sums, does the upper integral and the lower integral, do they actually coincide and equal the same number? If they do, in other words, this integral exists and equals a number, that number is what we call the volume of A. However, it's possible that, your upper integral and your lower integral will not coincide, in which case this characteristic function is not integrable over this domain. If that happens, we say that A has no volume. Be careful, because no volume sounds like volume 0. That's not the same thing. So it's possible, and we will actually see examples of this in just a moment, that this integral exists and equals 0. If that happens, the volume of A is the number 0. It's a number, it exists, it's 0. If, however, this integral just doesn't exist, because again, the upper integral and the lower integral, they don't meet in the middle. The upper integral is strictly larger than the lower integral. Then it's not that the volume is 0, it's that the volume just doesn't exist. We say no volume. We are going to go through several examples now, mostly actually on the number line. So A will be a subset of R. That might surprise you because I've been talking about a subset of Rn in higher dimensional space, but it turns out you can see some interesting behavior emerge just if you look at sets of real numbers. So I will show you examples where the volume is 0, where the volume is a positive number, where the volume does not exist. The set A has no volume. We will also see examples from domains which are higher dimensional than subsets of R. We will wrap up at the end of this lesson discussing whether or not we actually like this definition, or maybe we might want to see some different behavior. Our first example will compute the volume of the unit interval as a subset of R. So don't be too attached to the idea that the word volume must apply to like a 3-dimensional blob, because we will use that word in a general setting. Here it might feel more comfortable to use the word length or something like that, but we are still going to set up and evaluate the integral of the characteristic function of this set as a subset of R. For some of these examples, you might immediately see what happens. So you might look at that and say, it makes sense to associate to the set a size measurement of 1 as a subset of the real number line, but I would like to use each of these examples as also an example of checking ideas from integrability. So even when an example that we look at in this lesson feels obvious, let's try to set up and practice good arguments. Okay, so for this one, what I'm going to do is partition the unit interval from 0 to 1. Maybe I should point out by saying that this is already a nice rectangle on R. So that's not something I would necessarily write down in a formal context. But what I mean by that is the first step of taking our starting set and enclosing it in a nice rectangle is already really done for us because we're just going to work with 0 to 1 as the entire set. So 0 to 1 is a closed bounded interval on R, and that is the appropriate form of a nice rectangle on R. Okay. I worry sometimes that trying to mix these words together makes it worse instead of better, but I hope that you agree with me that this is the idea of a rectangle situated on the real number line. To prove integrability here for the characteristic function of this set, what I'm going to do is create a partition which only has 2 points. So this is the partition. It defines one subinterval, the entire domain from 0 to 1 itself. Let's compute the upper sum and lower sum of the characteristic function for this set with respect to this partition. Okay, so the upper sum of the characteristic function of the set with respect to this partition, which we just gave. I don't need to write sigma or anything like that because our partition defines just one subinterval. So it's going to be the supremum of the characteristic function on that set times the width of the subinterval. I think I will write that out in full detail for the upper sum, and then we'll probably skip it for the lower sum. We'll just say it out loud, but it's the sup of the characteristic function evaluated on the one and only subinterval defined by this partition. And then times the solo subinterval width that we've created with our partition. Well, certainly there's a point between 0 and 1 which lives in A, and therefore the characteristic function takes the value 1. In fact, it takes the value 1 everywhere, but the sup of the set of outputs is 1 itself. And then the interval width is 1 minus 0, so that's 1. What about the lower sum of the characteristic function with respect to this same partition? Hopefully you recognize that the infimum of the set of outputs is also 1, same subinterval width. So skipping maybe some detail here just to save room, but you might want to add this to your own paper. Let me make a note here that this is also the lower sum for this characteristic function with respect to this partition. Okay, I have a partition of our domain now on which the upper sum and lower sum agree. They are literally the same number. When you see that, you're probably thinking, hey, that must mean integrability, and the integral of this characteristic function on that domain is probably the shared value 1, and that is absolutely true. Let me just write down explicitly why that has to be the case. Let's see, I think I can do it here. Thus, notice 1 is equal to this. So I'm going to kind of make a chain of what will actually be equalities. The lower sum that we've just computed is less than or equal to the lower integral. Remember that that's like a supremum of the set of all possible lower sums. So this is less than or equal to what we would call the lower integral for the characteristic function, which even before we know integrability, we know if this number exists, so does the upper integral because this function is bounded on our domain. And this is automatically true. So the lower integral of the characteristic function is less than or equal to the upper integral. I'm about to run out of room, so I'm going to drop down. And then kind of reversing the direction here, this is an infimum of the set of all upper sums. So this is less than or equal to the upper sum that we computed, specifically with respect to this partition, which we know to be 1. Okay, sorry about the kind of badly formatted mathematics here. Reading left to right, we have 1. This this pair of numbers and 1. Therefore, all of these less than or equal to signs must be equality because we start and end with 1. Therefore, these two numbers coincide, they equal 1. And now we can conclude, wow, I really did not expect to fill up the whole board for just this one set. I'll try to be a little bit more efficient in the future examples. But we can now say that since these two numbers coincide, they are both the value 1. The characteristic function of this set, over this set, this integral exists and it equals 1. And that is exactly the computation that we need to conclude that the volume, as we've defined it just a moment ago, is 1. Okay, this was kind of a lot of work for something which might have jumped out at you as intuitively true right away. But again, I wanted to take the opportunity to say, like, let's make a partition, let's compute an upper sum, a lower sum, and then show integrability is literally being satisfied. We will look at a few more examples, and again, I'll maybe try to do them a little bit more efficiently than this one. The second example will be to compute the volume of any finite collection of points as a subset of R. So again, we're looking at a subset of just the real number line. I didn't name this set, so let's call this A. We want to compute the volume of A. Now, I think it's very likely that you know the answer or you have a good intuition about what the volume of this set should be, but I would like to take this opportunity once again to kind of rigorously prove it, and in doing so, bring in techniques and ideas from our definition of Riemann integrability just for practice. Okay, so the first thing we need to do is take the set A and enclose it in a nice rectangle, which again, on the real number line, just looks like a nice closed bounded interval. So let me start by just choosing 2 points, little a less than b, so that the set A is contained in the closed bounded interval from little a to b. Sorry about overusing the letter A, but it just sticks with traditional notation. Okay, so this is like the set S that I sometimes refer to. I think I'll leave that notation out. I think the next thing I want to do is actually go ahead and establish what the lower integral for the characteristic function of this set is, because it is pretty easy to see. Okay, so I think I want to go ahead and say, here's the lower integral. Jumping straight to just the lower integral isn't necessarily always going to be the second step, but it works out well in this case because we have these discrete points. I don't know how many there are. I don't know how many there are, but I do know that it's a finite collection, which means that I don't have any intervals belonging to A. Consider any partition. Do I want to say that? Yes. Consider any partition of this enclosing rectangle or interval in this case. As the set capital A contains no intervals, an interval would have uncountably many points. For each subinterval created by our partition, I'll just say for each subinterval, there exists a point which is not an A. All right, there exists X in a complement. Thus, the lower sum of the characteristic function of A with respect to this partition, maybe I should give it the name P so that I can use that here. The lower sum of the characteristic function of A with respect to this random partition for which we provided no details is going to be 0. Okay, so it would be a finite sum. Once you've created a partition, you create a finite collection of subintervals. So this is some finite sum of 0 times delta xi. 0 here because the infimum of the characteristic function must be 0 because there is at least one point, in fact, there are many, in each subinterval which does not belong to A. So the characteristic function is 0 on all such points. Okay, so that's 0. This is true for any possible partition, so I can immediately take the supremum of the set of all possible lower sums with respect to all possible partitions. It must be 0. So the lower integral, oh, I wrote f, but I meant the characteristic function of a is 0. And while I might have used a lot of words to say this, it's something that I think you probably immediately saw, which is that if I have the closed bounded interval from a to b, and I have some collection of finite points in here belonging to a, like this. So say these orange points are a. No matter how I partition this, every single subinterval has to have a point which is not one of these orange points because there are only finitely many, and a subinterval consists of uncountably many points. So for each subinterval I pick, there is an input which does not belong to a. Therefore, the characteristic function takes the value 0. The characteristic function is either 1 or 0, so I can say its infimum on each subinterval is 0 times the width of all the subintervals. We don't know what they look like, but it doesn't matter because this sum is going to be 0. True for all partitions, so the lower integral is 0. That means when I come back in just a moment, I will have erased this, and we will think from the other perspective of upper sums and the upper integral. That's a little bit different because, of course, in this picture, we can see that there are places where the characteristic function is going to jump up and take the value 1, like that. So I can't immediately have the same type of global statement that we had here, but that's something that we will address in just a moment. To reclaim some of the board, I've just erased all that work and written that we've now shown that the lower integral of the characteristic function of this set is 0. That means that if the volume exists, we know that the volume would have to be 0, but we're not ready to say that yet because we need to consider the upper integral. To do that, I'm going to use an estimate involving an epsilon measurement because, again, I erased the diagram, but I'm going to motion edit anyway. In the diagram that we were looking at, we know that there are places where the characteristic function is going to pop up. So therefore, we're going to have places where this characteristic function takes the value 1, which means I'm not going to partition it and land exactly on 0. However, we can try to bound above with epsilon, and that's going to be our way of addressing this. So first, let's let epsilon be greater than 0. Now, for this choice of epsilon, what we're going to do is design a partition so that the upper sum of the characteristic function with respect to that partition is less than epsilon. Since we are designing just one particular partition, let's make it a nice, evenly spaced partition. It will work out for us. Let's call the number of subintervals capital N, and let me give you a specific way to do that. So how about choose some natural number capital N so that this natural number is greater than, it's going to be twice the number of points, and I'll explain why in just a moment. So 2k times the width of the subinterval divided by epsilon. Okay, that is the number of subintervals that we are going to form. What we're going to do is take the interval from a to b and just chop it up into this number of evenly spaced subintervals. So now create, let's use the language of Riemann's condition. So we'll call it p sub epsilon. Create a partition p sub epsilon of equal width subintervals we could actually be more specific and say that there are n of these. So the n equal width subintervals, they'll have the same width, so we can call that delta x. And how you do this. So if you haven't created a partition in a while, what you do is you take the width of your entire domain, so that's b minus a, that's the width, and just divide it by the number of intervals that you're looking to create. So if capital N was 2, we're saying half the width of the original domain. If capital N was 3, we'd be chopping it into thirds. In reality, capital N is probably much larger. And in particular, what we can say is that delta x is literally b minus a divided by n, but that, by construction, is less than, let's see, bring n over epsilon divided by 2k. It's less than epsilon divided by 2k. Okay. Let me explain where this 2 is coming from. You might not be wondering, epsilon seems normal, k seems normal. We often cut things in half. There's actually a reason why I've brought in this factor of 2. So let's picture the domain again, going from A to B. And perhaps I have a family of points that looks like this. Okay. Yeah, that's fine. How many subintervals might contain one of these points? Well, let me give you just one possible partition. It might not be perfectly evenly spaced, but let's imagine our partition looks kind of like this. Not necessarily drawn to scale. It's important for us to know how many subintervals may contain one of these points, because if a subinterval contains one of these points, then the supremum value for the characteristic function of A would be 1. Everywhere else, it would be 0. So the characteristic function takes the value 1 over subinterval if and only if it contains a member of this family of points. So at first glance, it looks like the answer is k. Here, k is 3. So it's like, okay, I have 3 points. So there may be 3 intervals that contain one of those points, but actually it's 2k. And the reason why is you could have a partition of your domain where just kind of coincidentally, each of the points in this collection lands right on a slice point, and then each of your points would actually affect 2 subintervals. I don't think I actually realized that the first time I worked through this, but here you go. So it could be as many as 2k. It could also be 1. It may happen that all of these points occur right in here, and only one subinterval is affected by the existence of these points, meaning over only perhaps this first subinterval does our characteristic function take the value 1, and everywhere else it's 0, and that's going to influence our upper sum. But the worst case scenario would be 2k subintervals are affected by the points. Over 2k subintervals, the characteristic function takes the value 1. I hope that makes sense to you. Let's now take like this worst case scenario and create an upper bound for what the upper sum of the characteristic function with respect to this partition could be. That whole discussion that we just had, I'm going to say notice, meaning like I'm hiding kind of all the analysis that we just did on scrap paper. Notice at most 2k subintervals can contain a point from A. So I'll say at most 2k subintervals defined by this partition can contain a point from K, of A, rather. Okay. Again, that's the whole discussion that we just had. What can we now say about the upper sum of the characteristic function of A with respect to this partition? Well, therefore, if I started trying to compute it, what we would find is that over any subinterval which contains a point from A, the supremum value for this characteristic function is 1. So if we write out the sum, all of those would say, okay, the sup is 1 times this with, let me just write delta x for now. And then every subinterval that doesn't contain any of these k points would have a sup value of 0, because the characteristic function would be constant 0 over the entire subinterval. So it's like, how many times might you end up adding this positive expression to itself? At most 2k times. So I'm going to say less than or equal to 2k times this. Let me kind of point out what everything is. This 2k comes from this observation, and then this is like the sup of the characteristic function times the width. Okay, so when we write out the upper sum, of the upper sum of the characteristic function with respect to this partition, every single expression is either going to be 1 delta x or 0 delta x. It's like, don't worry about the zeros. How many times could you have a 1? At most 2k times. But now we can take delta x and go up in size by replacing it with this upper bound for delta x. So let's say strictly less than 2k times 1 times epsilon divided by 2k. And that, of course, is epsilon. All right, I'm about to erase this. Let me just say a quick remark and then I'll let you digest it. We'll finish the exercise in just a moment. To summarize what we've just done, we created a partition of the interval from a to b on which the upper sum of the characteristic function of a over our partition is smaller than epsilon. And we did that by considering this kind of worst case scenario for how the points are situated relative to our slices, basically. Okay, think about this, then I'll come back and probably condense this all down into another item over there, and we will finish this problem. What did we just show? We proved that for any epsilon greater than 0, there exists a partition. All right, there exists a partition of the closed bounded interval from a to b so that the upper sum of the characteristic function of a with respect to that partition is less than epsilon. So for any epsilon greater than 0, the upper integral, being the infimum of the set of all possible upper sums, is also less than epsilon, because if anything, it's to the left. Thus, for any epsilon greater than 0, the infimum of the set containing these numbers, also called the upper integral, is less than epsilon. But the characteristic function is a bounded function. This is a bounded set, so we know this number exists, and we know it's bounded to the left by the lower integral. Oh, sorry, again, I wrote f. Kind of muscle memory here. Let me change this. We have the upper integral of the characteristic function is greater than or equal to the lower integral of the characteristic function, which we explicitly computed was 0. So since epsilon is arbitrarily small, that must mean that this upper integral is 0. So once again, we have shown directly that the upper integral and lower integral have the same value. Their value is 0. So I'll write over a to b. So I'm like, this is the domain of my integration. And what am I integrating? The characteristic function of this set. This integral exists and it equals this shared value of 0. So any finite collection of points on R has a volume of 0. Let's think a little bit more about collections of points though. So we'll do a few more examples with points. They're not going to be a finite collection though, because we just established that any finite collection has a volume of 0. Here we have a set consisting of countably many discrete points, although the cardinality is infinite. So this is the Archimedean set. We would like to compute its volume as a subset of R. First step is to enclose it in a nice containing interval. A good choice would be just 0 to 1. Okay, so that's our enclosing rectangle. Take a moment on your own to think about whether or not the argument that we made in the previous example about the lower integral of the characteristic function of a, whether or not that can be adapted to this context. The answer is yes, it can. So let me write that down, just the statement. Similar to before, the lower integral of the characteristic function of a is 0. For a rigorous justification of this statement that I will just say out loud but not write down, a consists of points which are only rational. So there are no irrational points in A. But if you take any partition of this domain and look at the subintervals you create, by density, they must all have at least one irrational. In fact, they have many. So the characteristic function of A will be evaluated on an irrational number within each subinterval. So its infimum value is 0. That's true for every subinterval, so that when you add up any possible lower sum, you'll get 0. Okay, so that's just one way to explain this equality. Just like before, now we need to turn our attention to the other side and think about the upper integral. I'm going to do it a little bit differently, though. So for a picture of what's going on, here's the unit interval from 0 to 1. Okay, 1 itself belongs to A, then a half, a third, a fourth, a fifth. When we look at these points, well to the right of 0, they are just discrete points, and it kind of looks like the example we just did. What happens, of course, with the set is that we cluster up at 0. So what we will do is break our analysis into two pieces. Let me, as soon as I draw any kind of slice to the right of 0, I'm enclosing infinitely many points from A within that one single slice, and then for the rest of the domain, it's only finitely many. So imagine just dropping a slice here at a number epsilon over 2, where I'll write down let epsilon be greater than 0 in just a moment. Here, on this side of the domain, we can cite the prior result. I will do that precisely. I'll say how we're going to use it. But here, when we look at this half, it's not exactly half, but this chunk of domain, A presents us with only finitely many points. So we know that the volume of that set is 0. The characteristic function is integrable over this subdomain, and its integral is 0. Here, we have infinitely many points, but this is where all of the issues are happening. And if I imagine that this slice is very narrow, then I'm going to be able to neutralize the gap in the places where our characteristic function takes the value 1, which it certainly will, and also 0. So we have a sizable gap right here in the values, the outputs of the characteristic functions, but we can offset that by enclosing all of this behavior within just one subinterval with epsilon over 2. So it's like height difference is large, but make the base narrow. That's the general principle. Okay, so let's write this down. Let epsilon be greater than 0. And, it would be silly if epsilon was 10 or something like that. So typically you imagine epsilon is really small, just to make sure that, you don't pick an epsilon for which this diagram doesn't resemble your work at all. Let's make epsilon between 0 and 1. Okay. On the domain from epsilon over 2 to 1, we have only finitely many points from A. What's a nice way to say that? Notice the volume of A intersect epsilon over 2 to 1 is 0 by the previous result. Therefore, the characteristic function of A on this domain is integrable. We know its integral is 0. And in particular, I'm going to go the reverse direction with Riemann's condition. I'm going to use our knowledge of integrability to say that there is a partition of this side of the domain, which realistically, we should imagine it kind of enclosing the points of A in very little narrow subintervals. Okay, get the idea? So I'm going to use our knowledge of integrability to say that such a nice partition does exist. Okay, so by Riemann's condition, for integrability, there exists a partition P, I'll just call it P, of epsilon over 2 to 1, so that the gap between the upper sum and the lower sum of the characteristic function with respect to this partition is actually as small as you like. So I'm going to say design the partition so that the gap between the characteristic function with respect to that partition, the upper sum and the lower sum, is less than actually epsilon over 2. So it's like have this in mind and then go make your partition. Well, we know that this is actually 0, same argument that we've made several times. Notice this implies that just the upper sum is less than epsilon over 2, as the lower sum is 0. Okay, this marker is ready to be retired. I just erased the picture I'd like to point at, but we actually now have partitioned what you could think of as really most of the domain. If you remember what we were looking at together, to create the partition of 0 to 1, all I'm going to do is just add 0 into it. And since a partition, you think of it as a collection of points, we can say, now let the partition that we are actually going to finalize our computation with be what we were just looking at together with 0. So it's the union of this point and the collection of points beginning with epsilon over 2, chopping all the way through 1. I hesitated for a moment because it's a little tricky here with this division that we've done in the domain, but what I'm going to do is just say, by construction, here's what the upper sum of the characteristic function with respect to this partition has to be. So by construction, meaning look back at how we've done this. Okay, so the upper sum of the characteristic function of A with respect to this partition, it's going to be this first piece plus the rest of it, which we've already done here. So let's say the sup of the characteristic function for x in that first little subinterval between 0 and epsilon over 2 times the first width, which is epsilon over 2, plus, and now here's where I was hesitating, but I think I'm just going to go ahead and write this. All right, well, this is 1. This is epsilon over 2. This is actually strictly less than epsilon over 2, so we are going to go up in size here and replace this with epsilon over 2, which of course is epsilon when we add it together. So now I've glued those two sides of that division line together. On the left-hand side, we have a quite large gap. So 1 is the sup of the characteristic function here, but we've squeezed all of the bad behavior inside of a subinterval which had very narrow width. Epsilon over 2, you can make it epsilon over a million. I mean, as long as you make that first subinterval very small, you're going to contain most of A, all but just finitely many points. So that's being addressed here. And then it's like the rest of the partition is well behaved because we've already established that the volume of the set to the right is 0. Okay. I think at this point, I will probably stop this example because the rest of it will be identical to the exercise we just did. So let me just summarize out loud what we should now write down. Well, I'll write down one more thing. So the upper integral of the characteristic function with respect to A is going to be 0 just like it was a moment ago. Because once again, we are now saying that for any epsilon greater than 0, the upper integral is between 0 and epsilon. So that's exactly the argument that we just saw. Therefore, the upper integral is 0. And now we have exactly the computation we had a moment ago. Lower integral and upper integral are both 0. So the integral of the characteristic function exists. This is integrable over this set, even though it has infinitely many points in it. So if you think about the characteristic function as a function, it has infinitely many points of discontinuity between 0 and 1, because it's going to pop up to 1 every time it lands on a point of A. Otherwise, it's 0. Okay, I think I want to spend a little bit more time with that idea, so let me erase this. I'll just sketch the picture that I erased a moment ago one more time before we look at another example involving a collection of points. As I was wrapping up that example, it occurred to me that we were really observing a behavior that some of you may have never seen before, so I wanted to kind of shine a light on it. Here is a computer-generated image of the characteristic function of the Archimedean set plotted as a function of 0 to 1. What we have just worked out is that if you just think about like doing this in single variable calculus, which you probably did not do, if you integrate from 0 to 1 this characteristic function, I mean, you're not going to anti-differentiate it, right? So I don't think that you've seen this before. This integral, we now know, exists and equals 0. What's special here, what I wanted to lift up for you, is that this function has infinitely many jump discontinuities, and yet it is still integrable. That's not something that you might have encountered. Maybe you did in a prior analysis class, and I just want to remind you of that. For others of you, it might be the first time that you thought about this. But if you have, say, a continuous function over an interval like this, it is Riemann integrable. So is a function with at most finitely many points of discontinuity. So if you have a function which is bounded, so no vertical asymptotes or anything like that. But you've got finitely many points of discontinuity here. There are two jump discontinuities in this picture. This function would still be Riemann integrable over a closed bounded domain. It has area under the curve. But here's an example of a function which does more than this. We have infinitely many points of discontinuity, and yet it is still integrable. This is our first example of a set which has no volume. The characteristic function of this set is not Riemann integrable. It really goes down to density of, say, rational and irrational numbers. Here's a nice proof of the statement. Let P be any partition of the enclosing interval from 0 to 1. By density, we know that the characteristic function takes the value 1 on every subinterval because of the density of rational numbers, but also it takes the value 0 on every subinterval because of the density of irrational numbers. So by density, there exist rational and irrational numbers in every subinterval. So there are both rational and irrational numbers there we go, in each subinterval. Thus, there's no mystery for what the upper sum and lower sum of the characteristic function with respect to this partition, which is totally unspecified, what they look like. I'll start with the lower sum. Let me say in subintervals where that's not specified, so I can write some indices down. So going from I equals 1 through n, indexing across however our partition looks. I'm going to go ahead and jump straight to putting in 0 for the infimum, like that. Okay, so every subinterval contains an irrational number, which means that the characteristic function takes the value 0 on every subinterval. It's really a minimal value, but to use the general language, that's the infimum of the characteristic function over every subinterval. So we get every possible lower sum is 0, but every single subinterval also has rationals. So when I think about the supremum for the set of outputs of the characteristic function, that's going to be 1. Here, 1 times the sum of all of the widths. So basically, this comes down to add up the widths of the subinterval starting from the left and ending on the right side of the domain. That's just going to give you back the width of the interval, which was 0 to 1. This is true for all partitions. So we know nothing about this partition, really. That means that the lower integral is 0, but the upper integral is 1. Since this is true for all partitions of 0 to 1, the lower integral exists, but it is not equal to the upper integral. Therefore, this function, the characteristic function of this set, is not Riemann integrable, so the set has no volume. Okay, there we go. Not volume zero. Volume zero is what we saw a moment ago with a finite collection of points or the Archimedean set. Those were examples of sets which had a volume and that volume was zero. This set has no volume. There is no number that we would reasonably associate to the volume of the set. We just can't even say that the set has has the property of having a volume. Okay, so the characteristic function is not Riemann integrable. What about the irrationals between 0 and 1? It would be the exact same style argument. I think at this point, we've probably done enough examples of sets on R, so let's just do one quick example for a set in R2. For our fifth example, we are going to look at one unit along the x-axis, this time as a subset of R2. So I really want to focus on like a nice picture to illustrate how to do a partition here. All right. The domain is R2, and we are interested in the subset which consists of all of the points on the x-axis between 0 and 1. This set we already saw with our first example, I believe. We said that as a subset of just R, so if I forget the y coordinates here and I just looked at the real number line, this had volume 1 as a subset of R, but now we are in a different ambient space. This is the same line segment, but now viewed as a subset of two-dimensional space. So we are working in R2. Let's do some of the work here on this graphic again. I want to focus on visualizing this correctly. This was already a nice rectangle on R. So this was a closed bounded interval. That's the type of domain that we like to work on R, but it is not the type of domain that we want to work on R2. We need to enclose this inside of a proper rectangle in R2. It doesn't have to be in the interior of the rectangle. So these rectangles are closed rectangles. They include their boundaries. So I'm actually going to just grow this into the unit rectangle like this. Okay. So this is the set A right here. You know what? I think I'm going to probably draw inside this. So let me move this below. Okay, so here along the x-axis, we have our set A that we are considering. This square is what we've called in our study of Riemann integration S. So it's the nice enclosing rectangle which has sides parallel to the coordinate axes in R2. Again, it's okay that A is on the side because S is a closed object. It includes these boundary line segments. I want to create a partition of S that will allow me to compute the volume of A. What I'm going to do is I was thinking, should we do the lower sum first? Let's just go straight to letting epsilon be greater than 0. Let's create a partition of S. And all I'm going to do is actually tack on here that epsilon is also less than 1, just so that the picture matches up to the arithmetic. I'm actually going to put just one horizontal line here at epsilon over 2. My division by 2 here is just to ensure at the end that if I want to have strictly less than epsilon, I will probably be able to get it, whereas if it was just epsilon, I might end up with equality. Okay. All right, this is subdividing now S into two rectangles, this one and this one. So it's a very basic partition. I've just added one slice perpendicular to the y-axis. Here's how you can write this as a set. It's a Cartesian product of sets. Let P sub epsilon be the Cartesian product of any slices you made along the x-coordinate. Well, I'm just going to go from 0 to 1. So these are the x choppings. And then the y choppings here, we are going from 0 to epsilon over 2 to 1. What this Cartesian product does is it defines 6 lattice points for this partition of S. So in particular, we're going to take this 0 for the x-coordinate and say 0, 0, 0, epsilon over 2, and 0, 1 are points, giving us corners of our partition subrectangles. So that's here, here, and here. So these 3 points are partnering up 0 with the coordinates from the second set. And then same thing, 1 cross this gives us this point, and this point. If I had made a slice in the x-coordinate, I would have another coordinate here, and it would give us 3 more points for a total of 9 points. Okay, so it's like the x-coordinates cross the y-coordinates. This is defining this partition of S. What are the upper and lower sums of the characteristic function of A, that's set down here, with respect to this partition? I'm not going to write out like a whole proof with words. Let's just do the computation. If I look at, say, this subrectangle, let's call this one the first one, and then the second one, the subrectangle, it's a rectangle in R2, so it's more than just a line segment. In particular, there's a point up here where we are not in A. And there must be such a point because the height of this rectangle is a positive number. So certainly the point 0 epsilon over 4, even epsilon over 2, must be included in this first subrectangle. So there's a place where the characteristic function must be 0. So that's 0 times the volume of this first piece. So the volume of, let's call it S1, is width times height. So that's just going to be 1 times epsilon over 2. And the volume of the second piece is, again, 1 times height, which is 1 minus epsilon over 2. So that's the height times the base of 1. Okay, so for our first subrectangle defined by this partition, we have an infimum value of 0, because certainly we are not identically 1 on this subrectangle, times the volume of the subrectangle, which we know now to be base times height, epsilon over 2. And then up here, every y-coordinate in this second subrectangle is above the x-axis. So the characteristic function of A is identically 0 on this second subrectangle. So this is also 0. Okay. Let's do the upper sum of the characteristic function with respect to this partition. Now, if I look at this first subrectangle, there are plenty of places where the characteristic function is 0, but there are also infinitely many points down here on the x-axis where the characteristic function is 1. So we do attain 1 on the first subrectangle times the width of epsilon over 2. But up here, we have no points of A. So the characteristic function is identically 0. The sup of the outputs of the characteristic function is also 0. So overall, the upper sum of the characteristic function of A with respect to this partition is 1 times epsilon over 2. Okay. And again, I cut epsilon in half here just to have an inequality. Thus, the upper sum minus the lower sum with respect to this partition that we have is equal to epsilon over 2, which is less than epsilon. By Riemann's condition, that tells us that the characteristic function of A is Riemann integrable over A as a subset of S. It's Riemann integrable, therefore the volume exists. What is the volume? I'll leave you to work out in details, but can do a similar argument as we've done before. Any partition you make of S has to have proper rectangles, which means you can't have a degenerate rectangle that looks like a line segment. You have to have rectangles here which have volumes greater than 0. So no matter how you slice up S, say your bottom subrectangles that touch the x-axis, they must have a height to them. So there are going to be y-coordinates contained in every single subrectangle defined by any partition of S where the y-coordinate is positive, which means that all possible lower sums will be 0, so the lower integral is 0, so the overall integral is 0. I did that fast because this argument kind of repeats something that we've done a few times. What I really wanted to show you was what the partition looked like and how to notate it. I also want to just point out that this set had volume 1 as a subset of R, but it has volume 0 as a subset of R2. Let me just give you a quick exercise to think about for a second. The square, if I looked at this square S and that was my new domain, that has volume 1 as a subset of R2. It has volume 1 as a subset of R2. If I took this exact square in the xy plane, but now embedded it in R3, so we had, if you can see this little picture, the unit square in the xy plane now embedded in R3, what would be its volume as a subset of R3? And hopefully you realize the volume would be 0. So here it's 1, but here it's 0. So it's not enough to take the set on its own. You always need to think about where is the set living. It matters. So here, the fact that this segment along the x-axis was in R2 meant that the volume was 0. Likewise here, the same line segment in three-dimensional space would have volume 0. Okay, that wraps up the examples. I want to make a few more remarks before we close this lesson. We are almost done with this lesson on volume of sets, but before I let you go, I just want to point out some kind of like limitations of our definition of volume that you may have already honed in on, because I think it partly motivates our next topic, which is measure. So volume has some kind of lack of additivity that I want to highlight here. And it doesn't mean that we need to go back and change our definition of volume. Our definition of volume is the definition of volume. It's just that it's not a perfect definition because it has these kind of quirky behaviors. So the first one, what I'm trying to notate here, my first remark, is that the volume of any single point is 0. Any finite collection of points, the volume is 0. So certainly for one point, the volume is 0. However, it is possible to have a countable collection of volume 0 sets with no volume. So in particular here, it's like what I'm trying to do is say, take all the rationals and put them together between 0 and 1. That set has no volume. That doesn't mean that our definition of volume is bad. It's just, if you're thinking about taking unions of types of sets, you may have wanted to observe the property that any kind of countable collection of volume 0 sets has volume 0. That may have been a conjecture that you made early on in this video, and it turns out that that's not the case. And passing from a single rational to all of the rationals between 0 and 1 is a counterexample. Similarly, we have this statement I've written here where I'm trying to point out that between 0 and 1, the rationals have no volume. Likewise, between 0 and 1, the irrationals have no volume. So neither of these two sets has volume. You can't associate a volume to them. And yet, if you take their union, the volume becomes just the volume of the unit intervals, a subset of R, which we proved has volume 1. Again, there's nothing to fix here about the definition of volume. I just want to point out these sort of additivity statements which just don't turn into global theorems. In part, when we look at measure next, it may provide a little bit more cohesion between these ideas than volume gave us. Okay, thank you for your attention. Actually, real quick before I let you go, in case you're reading this very carefully to see what I did here, it's all of the rationals between 0 and 1 except 0 itself. Turns out I didn't quite get to that one, but that's okay because that set also has no volume.